To demonstrate Kubernetes features, we're going to deploy two applications. The first is a server application, which is going to expose some endpoints over HTTP. We're using the built-in HTTP server that's part of the JDK, so we won't need any external dependencies for this. Its API is a little bit verbose, but quite simple. You can see we're exposing three different endpoints, one called /ready, one called /alive, and then for the root path, we're just returning a string response, which is hello from server app. We'll be going into some details about what readiness and liveness is inside Kubernetes, but we won't go into that in this video. We've got a little utility class called string response, and all that does is return a HTTP code of 200, which is okay, and then it writes the stream to the output stream. So basically from a ready, we're going to return the string ready, status code 200, then the same for alive, and then this custom hello from server app for the root path. We're going to use our standard Docker image, so there's nothing new with Docker files for this talk. So that's the code for the server application and the Docker image. Let's look at the deployment. So it is the same as the one we used in the slides. We're going to have two replicas and we're going to expose port 8080, and that's going to be where we can hit the app and return HTTP. We're going to make one modification, which is purely because we're running in Minikube rather than a real cluster. We're going to set the property image pull policy is never. And the reason for that is we're not going to push our images to some global repository that our Kubernetes cluster has access to. Instead, we'll just be pushing our images locally. And because we've done the Minikube Docker M trick, those images are going to be available to our Docker cluster. So let's publish the images now. So we're just going to run our normal command, which is the Gradle Docker command, and that will make the images available. We can validate that by running Docker images. Okay, there's a lot there, so we just run Docker images -head, and we see the most recent one, and we can see we've got the server app, which is the code that we've just looked at. Now it's time to run our first Kubernetes deployment. So let's just cat the deployment file to remind us what it looks like. And there it is. We've got the image pull policy to never. We're publishing the server app image. We can see there's no pods before we've started. But what we're going to run is kubectl apply and then the deployment, and then it's done. So we can now see whether that's worked by running kubectl get pods, and you can see they're running and they're ready. Kubectl has a neat trick. It's got completion built in. So we can run this command, source, kubectl completion, and then Z shell or bash, depending on which shell you're using. And then we're going to get completion for resources like pods and deployments, and we'll get completion for active things. So here I didn't have to type the whole server app deployment and then the identifier. Instead, I can get completion. And from the logs, we can see that the server has started. And that's the only logging that that server does. Now that we've got an actively running deployment with some pods, we can use kubectl describe to see some information. We can see that it's exposed port 8080, which is from our deployment. And we'll see that each pod does get an IP, which is shown here, but we're not going to address and use those IPs directly. Instead, when we come to access this service from a client application, we'll use a Kubernetes service. Another interesting thing is the quality of service class. We've got best effort, and that means that is because we have not given any resource limits or requests. And best effort means that this pod, these containers, they're going to only get the resources not used by other pods and containers that have set requests. Before we hit the application, let's demonstrate what happens if we delete a pod. We've asked for a deployment with two replicas. So if we were to delete one of these pods, then Kubernetes will fix it for us. We can see here that one of them has been deleted, but before we could even run kubectl get pods, it has been recreated. And we can tell this if we look at the age. The original pod has been around for 86 seconds, whereas the one that's been created in response to us deleting a pod has only been around for a few seconds. To see the status of a deployment without just looking at all of the pods, of which there might be many, we can describe a deployment. So let's look at what the output of that is. And you can see it tells us all about the replicas. How many there meant to be, how many there currently are. Now this could be lower than the desired because there might not be room on any of the nodes. Some of them might be pending. The updated part, that is to do with rolling redeploys. If we ask for Kubernetes to deploy a new version of our deployment because we've, say, released the next version of our application, by default, it will do one pod at a time. And it updates the updated so you can see how far through the rolling redeployment it has gotten. Now that we've got a server application up and running, we need to see a client application that's going to hit that application. So let's have a look at this. It's in the Kubernetes Client App submodule of the samples project, and it's a little bit simpler. It is just a main method that discovers a host and a port from environment variables. Remember that when we create a Kubernetes service, all of the other pods and services, they get the host and the ports of that application injected as environment variables. The only thing we're going to do in this client application is hit the server application, sleep for 5 seconds, and then do it again. And we're going to keep doing that. So this client application will never end. It will just keep hitting the server application. Like with the server application, there's nothing new in the Docker file. It's just adding the application and setting the entry point. Let's just change the base image to slim, so it's a bit smaller. And let's have a look at the deployment for this application. So the only difference between this and the server application is we're only going to have one replica. We've specified image pull policy like we did with the server application. And this client application doesn't expose any ports. So we don't have that section. Before we deploy the client application, we need to create a service which points to our server app deployment. Otherwise, those environment variables which we were utilizing will not be set. This is what the service looks like for the deployment app. The important bit to get right here is the selector. That must match the labels that we've put in our server app deployment. To show this, let's just open these side by side. So let's pull the deployment open and make these a bit bigger. And then reopen the service. And we can see in the service on the left here, we've got selector equals server app. And in the deployment on the right, we've got the label equals server app. So that's how these two things match up. The other important part is the other ports. We want to expose port 80 because that is the port which people expect to HTTP to run over, but our server app, like lots of common Java web frameworks, has exposed port 8080 instead. We use the same command to create the service inside Kubernetes. We use a kubectl apply and then just pass in the service.yaml. We can then list the services with kubectl get services, and we can see there it's been allocated a virtual IP. This IP will be the same until we either delete or recreate the service. So this is the IP that is going to be injected via that environment variable. Pods will come and go, and they're going to get different IPs each time, but the service IP always remains the same. The next step is to deploy the client application. So for that, we need to jump into its directory, build the image, so the image will be available inside our Minikube Kubernetes cluster, and then use kubectl apply to create the deployment. So let's quickly run that. And that's done. So now we can kubectl apply for the client deployment. So that's in the Kubernetes Client App /deployment. So now we have a server app and we have a client app, and they should be communicating via a service, or the service discovery happens via a service. We can see they're all there, and we can do a logs, and the client application has already hit it 3 times. we can see it says hello from server app, which is what the server app returned for the root path. There's no logs in the server application. The last thing that we're going to demo is how to achieve ingress. And that means that we're going to send a request from outside the server. Remember that services are for when you want to do service discovery within a cluster. We have to add on the ingress step if we want to access the service from outside of the cluster. The ingress rule that we've defined for our server application is solely based off the host. So any traffic that comes into the Nginx index controller for our Minikube, if it's directed at serverapp.info, then it will be directed to our service. We can see the path, but that is /, so everything goes there. The way that it decides where to send that traffic is via the service though. We can see the service name is server app and the port is 80. So now let's create the ingress and then see how we can access it with a Minikube Kubernetes cluster. So we use the same command that we've used before, which is apply, and then we can use kube control get to make sure it's there. And for more details, we can use kube control describe. In there, we can see messages such as that the ingress controller has created our ingress. The last step is to see how we can access it. So if we just first cat the ingress.yaml to remind ourselves what host the ingress is expecting traffic on. So it's server-app.info. With Minikube, because it's running in a virtual machine, the ingress controller is running on the virtual machine. We can find out the IP of that with Minikube IP. We can then use that command inside a curl command to go through ingress via our service and into our server app. I'm going to run curl -v and then http, run the Minikube command to get the IP, port 80. Now, as you can see, we get a 404, and that's because the ingress controller is not expecting any traffic to go directly to its IP. You can see in the verbose output of curl that the host header has been set to 192.168.64.3. So what we need to do is pass in the host header to trick this. We're going to pass in the host to be the expected host in the ingress, which is serverapp.info. With the curl command line, we can pass that in with -- header, and we just need to write it in there and then send the request. That should tell the ingress controller to forward it to our service. And there we have it. We can see that we get a 200 OK and that the response body is hello from server app, which is what we're expecting.